this video, we'll discuss control transfer instructions. Before describing the instructions, we'll discuss how the destination address can be calculated. The destination address is the address given to the processor to make a jump to. You can find in the literature the term near and far jumps. They are valid if the segmentation is enabled. The jump performed within the current segment is called near. The instruction modifies the instruction pointer only. If the address is provided in full logical form containing segment and offset parts, the code segment and instruction pointer registers are modified. Such an instruction can perform a jump between segments, and it's called far. As on 64-bit systems segmentation is disabled, so we will not go deeper into this topic. Assembler encodes the destination address as absolute or relative. An absolute address is given as a value specifying the destination address as the number of the bytes counted from the beginning of the memory. A relative address is calculated as a difference between the current value of the instruction pointer and the absolute destination address. It is provided in the instruction as the signed number representing the distance between the current and destination address. If it is possible to encode the difference as an 8-bit signed value, the jump is called short. Usually, an assembler automatically chooses the shortest possible encoding. Using relative addresses is the most common because it makes it easy to locate the program anywhere in the address space. Control transfer can be conditional or unconditional. Conditional transfer instructions check the state of the chosen flag in the flag register and perform the jump to the specified address in the condition. Gives a true result. If the condition result is false, the processor goes to the next instruction in the instruction stream. Conditions are specified the same way as we discussed in the first video about instructions as a suffix to the main mnemonic. Unconditional transfer instructions are always executed the same way. They jump to the specified address without any condition checking. Let's describe the unconditional instruction first. The JMP instruction jumps to the destination address by putting the destination address in the instruction pointer register. The call instruction is designed to handle subroutines. It also jumps to a destination address, but before putting the new value into the instruction pointer, it pushes the returning address onto the stack. The returning address is an address of the next instruction after the call. This allows the processor to use the returning address later to get back from the subroutine to the main program. The ret instruction forms a pair with the call. It uses the information stored on the stack to return from a subroutine. Software interrupts instructions are also unconditional control transfer instructions. They are handled in a similar way to hardware interrupts. An interrupt mechanism in x86 works with hardware signaled interrupts or with special interrupt instructions. Return from an interrupt is performed by executing the iret instruction. In 32 and 64-bit architectures, the mnemonic for this instruction is iret-d. The iret instruction differs from the ret instruction with popping of the stack not only the return address, but also the content of the flag register. This keeps the content of the register unmodified after return and additionally prevents unintentional blocking following interrupts. A hardware interrupt can be signaled anytime during the program execution. That's why the current instruction is executed to the end, the jump to the proper interrupt routine, called also a handler, is made, having the information about the source of the interrupt. The processor automatically decides what the number of an interrupt and takes the handler address from the interrupt descriptor table. Such a descriptor is called a gate. Software interrupts are handled the same way as signaled by the hardware. The int instruction signals the interrupt of a given number. It is used in 32-bit versions of the Linux operating system to call system functions. Now let's discuss conditional transfer instructions. The conditional jump is a single instruction which can be used with many suffixes, specifying the condition. The list of suffixes we described in our first video about instructions. The JCC instruction is used to test the state of flag and performs the jump to the destination address if the condition is met. In modern pipeline processors, it is recommended to avoid using conditional jumps if only possible, ensuring that the program flows continuously without the need to invalidate the pipeline. It is important to remember that flags are modified as a result of executing the arithmetic or logic instruction, but not the move instruction. The x86 architecture offers a special loop instruction which is executed a known number of times. The number of iterations should be set before a loop in a RCX counter register. The loop instruction automatically decrements the counter register, checks if it reaches 0, and if not, jumps to the address, which is the argument of the instruction. This address is assumed to be the beginning address of a loop. If the counter reaches 0, the loop instruction goes to the next instruction in the stream. Please note that if the counter register is 0 before entering the loop, it can cause the system to iterate many times. As the first step is the decrementing of the counter, it will result in a value composed of all ones. For CX, the loop will be executed 6k times, for ECX more than 4 billion times, and for RCX 184 quintillions, 466 quadrillions, and really multiple times. Understandably, we should avoid such a situation. The JCXZ, JECXZ, and JRCXZ instructions can help to jump over the entire loop if the counter register is 0 in the beginning. There are also conditional versions of the loop instructions, which allow finishing the iteration process before the counter reaches 0. The loop E or loop Z instructions continue the iteration if the counter is above 0 and the 0 flag is set. The loop NE or loop NZ continues iteration if the counter is above 0 and the 0 flag is cleared. We can find on the internet the information that the loop instructions are not optimized in modern processors, and loops are quite often implemented with the compare and conditional jump instructions. Please watch other videos about instructions. For a detailed description of instruction groups and instructions, please refer to our Purple Book and AMD and Intel documentation.